Hi everyone, I'm Jun Hongjia from Computational Media Innovation Center at Victoria University of Wellington. It's good to see you all online in March 2021. Today I'm presenting our paper, Adaptive Lighting Estimation Using Dynamic Filtering for Diverse Lighting Conditions. This work is done by myself and my colleague Andrew Chalmers and Taiwan Ray. This work is aiming to improve the reconstruction of environmental lighting in mixed reality just based on a partial view images. Lighting is one of the key components to seamlessly blend virtual objects into a photograph for augmented and mixed reality. A rendered object that is too bright or too dark or lighted from a lighting direction that is inconsistent with other objects in the scene can immediately appear fake. To present a high-fidelity illumination for convincingly lighting synthetic 3D objects, a high dynamic range 360 environment lighting map is required. The problem is how we can get such high dynamic range 360 lighting map. A 360 omnidirectional capturing device can be used to obtain it, but such setups are often expensive and often go with massive post-processing techniques to get it to work. An alternative way is inverse lighting, which will reconstruct the global environment map from a limited field of view images based on the clues like the specular lights or the shadows that appear in that image. It's a low-cost way and will be more friendly for commercialized application. With the rapid development of the machine learning methods, this task will become more and more competitive. This paper, we will focus on machine learning-based inverse lighting. To reconstruct high dynamic range environment map from low dynamic range field of view image is a challenging problem, considering the diversity lighting conditions that can be captured by mobile phone. First of all, the field of view in a mobile phone image can only occupy 6%, less than 6% of the panoramic scenes, which means most illumination cues are invisible and need to make visual reasoning. Moreover, there are lots of lighting variations in the real world, especially for the indoor lighting. Considering the sensor or the lens characteristics of the capturing device, the captured luminaries can have varying field of view, exposure level, and color shift. It requires the inverse lighting can not only be selective to lighting-related features, but also need to be robust to these lighting variations. Recent methods that use deep learning frameworks to estimate lighting from photographs has tried to address different sub-problems within the field of inverse lighting. The seminal work was done by Gardner 2017, which used a CNN neural network to realize an indoor lighting estimation. Some follow-up work worked on the spatial varying indoor lighting estimation, which makes the estimated lighting become position-aware. Some prior work, like Jeffro 2017 and John 2019, are addressing outdoor lighting estimation problem, which often try to model both the sun and the sky lighting conditions in outdoor environment. John 2019 also tried to extend the deep learning model to make it be generalized to all weather conditions. Although many neural network structure has been proposed to address various lighting estimation problems, special consideration hasn't been given to the wide range lighting variations found between the environment and the camera response. As a result, they are not robust to the variations in camera characteristics across different mobile phones. In this paper, we propose a novel dynamic lighting neural network we call DLNet to address this problem. DLNet can estimate indoor environmental lighting and diverse input variations using limited field of view image. Specifically, we support high variations in field of view, exposure, and white balance of the mobile cameras. We will also show that DLNet has improved indoor lighting estimation compared to previous work. Our key idea is to build and train a deep neural network that is aware of the wild variations of the input photographs. To achieve this, we introduce a spherical dynamic filtering framework that adaptively generates the convolution filters that tailored for each input samples. As opposed to the traditional framework, where the filters are fixed after training and shared among all the samples. We impose a novel spherical multi-scale dynamic convolutional module, which we call the SMG module, onto multi-layers of the decoder. We also impose a multi-scale dynamic convolutional module, which we call the MG module, onto the feature extraction layer. The dynamic features that extracted from the dynamic convolutions are more selective for lighting-specific cues and improve the generalization of the lighting estimation. The aim of the SMG module is to model the discrepancy between the shared and the input customized lighting features. It consists of two parts: the dynamic filter generator and the dynamic convolution layer. The general feature map that is extracted from the backbone neural network will be used as the input of the dynamic filter generator. They will be transformed to the input customized dynamic filters, and these dynamic filters will be used as a convolution kernel and will be convolved with a general feature map in the dynamic convolution layer to generate the customized feature maps. For the training data, we use lava dataset as our training dataset, and we make the data annotation based on that. We create the data annotation by considering the wild variations of the lighting conditions that imposed by how the camera sensor responded to the environment. In our experiments, we use three properties that greatly impact the lighting and light estimation. They are color, temperature, exposure, and field of view. For field of view augmentation, we choose the range between 70 to 120. They are the most common field of views on popular mobile devices. For white balance augmentation, we use white balance emulator, which is a deep learning-based color augmentation method that is proposed by IPV 2019. The advantage of this method is it can accurately emulate realistic color consistency degradations, and the generated color shift is more authentic to the color case that caused by the real cameras. For exposure, we choose a reasonable range that between 0.25 to 2.25 as the under and overexposed cases. We conducted a pairwise comparison user study to evaluate how well our lighting estimation. Users will present pairs of images that contain virtual objects illuminated by lighting produced by our methods and one of the other state-of-the-art methods. Using the ground truth as a reference, participants were asked to select which image had a virtual object that is most visually similar to the reference. For the user study results, we make a statistical analysis using a binomial test. Here we show the user response ratios and their field of view variations, exposure variations, and color temperature variations. We can see that the majority of participants preferred our methods over prior work across all the three properties. This indicates that the DLNet can generate more realistic render results than the other methods. We use two measures to measure the important properties of the environmental lighting in our evaluation. They are directional lighting error and tonal lighting error. The directional lighting error measures the angular error between the nearest pairs of lights between the ground truth and the estimates. The tonal lighting measures the distance between the mean of the environment map in the LAB color space. Here we show our prediction study results. We investigate the contribution of using data annotation and the SMG module against the baseline network without either of them. From the figure, we can see that the data annotation and SMG module helps to reduce the metric errors on a wide range of variations. The combination of data annotation and SMG achieved the best performance on both directional lighting error and tonal lighting error. Here is one comparison with three other state-of-the-art works. In this comparison, we composite a mirror sphere and a glossy white sphere into an input paragraph. The predicted environment map by different methods are used to illuminate the sphere. We can see that our predicted environment map match the ground truth better and can get more convincing render results. Here we show some more AR examples. In this example, we test with 3 different phones with different field of views. As we can see that the lighting estimation can adapt to the changes of field of view, and the lighting directions was maintained across different phones. Here is an AR example and exposure variations. We can see that the shadow of the ball maintained accurate across different exposure levels. Here is an AR example and the different color shift variations. We can observe that the lighting estimation is robust and can maintain the lighting direction very well across different color shifts. To conclude, we present DL9 and a data augmentation strategy that can accommodate the wide variations of photographs. We achieve this by using SMD module that can adaptively generate convolution filters for each new input. We also make data augmentation to encompass the expected variations of lighting and sensors from the wild. As a future work, we plan to improve the loss functions to get more accurate lighting prediction results. And we also consider to improve the spatial and temporal consistency of the lighting predictions to make the model work better on the video input. Thank you for your attention.